All right, let's set the scene. Let's remember where we left off. Classification is the idea of guessing or predicting something that's categorical. So not like a number that has a range, like two like discrete things. So like for a self-driving car, hey, is this part another car? This pixel another car? Is it a traffic signal? Is it a stop sign? Is it a tree? This email, is it spam? Is it not spam? It's like 0 and 1, not 0, 0.25, 0.333. So many options, right? It's just two options, just a couple, all right? And so the way to make a class, there's many different ways to make a classifier, but really it's just a black box, and you've trained it somehow using some machine learning method. And so a classifier in a nutshell is you give it some attributes. You give it like the glucose and the hemoglobin for that chronic kidney disease example. You give it some inputs, and then you predict whether or not this patient with those readings for their blood sample got or had chronic kidney disease. And so that's all you're doing. You're making that red box or black box or blue box when I draw it with my pen. And the way that you create your classifier is you kind of train it. You train it by splitting up your data, because you got a nice good sample from your population. You got some nice labeled data. You know, for a certain set of people, like you took the time to get their blood samples, you took time to like have the doctor check them out and see if they actually had this CKD disease. And so you've got a bunch of samples and labels. You have the ground truth, we say, for those samples. And to train your classifier, you split it up. You snip up your good sample into a training set and a test set. And you build your red box or your black box or your blue box. You build your classifier with your training data, where you're trying to get it to learn what it means to have chronic kidney disease. You're trying to get it to learn to understand when there's a stop sign in the picture. All right. And that there's one way to do it that we talked about. We'll get into that in a second. And then you save away some of your labeled data to test. You save away a little bit of it. You don't give it to your classifier to train, because maybe it accidentally memorized stuff. You don't want it. You do not want it to memorize things, just in case you would like to make sure that it's not guessing things. So you keep some stuff away secretly, and then you test with that. You try to give it the attributes, and you see what your classifier gives back. And if it gives back the same thing as the secret label that you're hiding from it, then that means you trained a good classifier. So that's where we're going. That's what we did. We talked about one kind of way to make a classification engine. We made it the nearest neighbor classifier, which was we have a bunch of data already. We have a new thing that we're trying to make a prediction for. Go and plot that in our multi-dimensional space of stuff. Go plot it. And go find things around it. Go find like the nearest K things, right? Remember the word? The K nearest neighbors. Go find the nearest K things. See what their labels were. Did they have cancer? Did they not have cancer? Go figure out what was going on with them and let majority rule. That ended up being our goal. All right. So K nearest neighbors in a nutshell. You got your new point you're trying to predict values for. Go find the nearest K things to it using a distance calculation. And then sort by that distance, find the nearest K things, look at their labels. Look at their labels. We know how to find distance now. It's a nice Pythagorean theorem generalized thing. And this ended up being our algorithm. All right, this is our data set. If we set K to 3, set K to some odd number so you can have majority rule. You find the K nearest neighbors to this new point, like this Alice person. You're trying to predict, hey, did she have cancer? Did she not have cancer? Something like that. All right. So go plot her and go find the people next to her, the nearest K dots, the nearest K points in your data set. Could be multidimensional, that's fine. So you got to calculate the distance from Alice to everybody. But get those distances, get the closest 3 things, let's say, and then the closest 3 things have classes, right? They have labels. They're blue or green. They had cancer, they didn't have cancer. They had this disease, they didn't have this disease. And you see, like, okay, there were 2 blues and a green. So that means it's more likely in this area to be blue. So take a majority vote. We're going to predict then. We're not sure what Alice is. Like she's like some new patient. We're not sure, but we want to flag her. We're going to mark her as we're going to guess and predict that she was the blue class, which was maybe she didn't have the disease or something. Okay. So that is where we're going. And we would like to make this kind of function. We'd like to make it because we're looking for Alice, we're looking for this new point within our training data, because that's how we're building the classifier, based on our training data. All right, so we'd like to build this function called k-nearest-neighbors, take our training data, take the new point you want to go put in that, and find the nearest whatever things, and then you give the k value there, like nearest 3 things, nearest 1 thing, nearest 5 things. Always got to be odd, so that there's no ties. And then we give back what we predict this person to be based on this entire process. Okay, so that's k-nearest neighbors in a nutshell. Does it make enough sense? It's coming back. All right, so let's do it. Let's do this for this pretend person, k-nearest neighbors on Alice. So what we needed, we started this last time. Scrolling on down. Here was the process. K-nearest neighbors on Alice. What we wanted, right? We had our CKD table. Let me just play all this back. Here it was, chronic kidney disease table. We took out just we're going to use only hemoglobin and glucose to predict chronic kidney disease for people. And we know that Alice is this person. Alice has 0 hemoglobin value, 1.1 glucose value. We want to go find like the nearest 3 things to Alice in this data set. So go find the distance from Alice to this one, to this one, to this one, to this one. Yeah, that's what we did. And here's our distance function calculation. It kind of generalizes that idea of the Pythagorean theorem. And we made a function that finds the distance from Alice to any row of a table. You give me some row of a table, I'll give you the distance from this new person Alice to that row. So Alice is this. CKD is this. We want to just compare against hemoglobin and glucose values, so we'll drop the class. And like this is the row 0. If I go back to this before we called the function on it. This is row 0. We can apply our function to that row because it took a row and it gave back. Sorry, I need this function. I need all these functions defined, excuse me. So our distance from Alice function. Boop, boop. There we go. And this was able to find the distance from the first row, 11.2, 117, to Alice, and it was 116 units in this 2-dimensional space. Okay? And once we have this function, we can apply it to the whole table. Apply it to the whole table without the class. And look at what happened. We can find the distance from everybody in the table to Alice. And if we plop that back in the table, now we can sort by it, right? We plop this back in the table, we can sort by it. We end up with this situation where we've got this new column, and it's like distance to the new dot we care about. Here they all are. We can sort by it, find the top K. All right, that's our goal. That's where we're going. And then we can make a prediction for Alice by looking at the classes. All right, so that's where we left off last time. And let us continue. So let's see. These are the distances to Alice. Let's turn this into a function because we're going to need this eventually anyway. All right, so what did we just do? We kind of found all the distances from our training set to some new point. All right, so this will turn into a function. Give me all the distances using our training set to this new row that we're trying to figure out, like, what is the class label? What does this person have cancer? Do they not have cancer? So this is going to give back this idea of an array of distances to everybody from this new row to anybody in the training set. All right, so returns an array of distances between each point and the training set and the new point, which we're pretending is a row. All right, which is a row of attributes. We can convert it very quickly. That's fine. All right. So what an attribute is, remember, is just the stuff we're comparing against. So these are our attributes. These are what we're using to make a prediction. So the hemoglobin values and the glucose values, we're trying to predict the class for a new person based on those 2 values. So those are our attributes in this situation. So for our training set, usually you have the class label too, so you want to get rid of that when you do your comparison. All right. So the attributes only of this table is give your training set, and we'll drop the class label, assuming that it's always called capital class. All right. And what we want to do is we want to apply, like, we want to make our distance to Alice function again, kind of in here. but not distance to Alice this time. It's like distance from Alice, distance to a new row. Okay, that's what we want. Distance from new row, which is just that, right? Find the distance from this new row to whatever row you're looking at right now, please. And here I am within a function making another function. That might make you a little uneasy. That's okay. That's allowed. You can make functions inside other functions, and they can use things from the outside. So like this function is using this new row, which was a parameter of the outer function, which is cool. But we need this. This is like our distance to Alice. They can use outer variables. Cool. We like that. And then how do we generate this array of distances from everybody in the training set to this new row? Well, we take our attributes. We apply this function that calculates the distance to every row on every row, because that's what happens when you apply. This will give me back an array of all of those distances, and I can return it. Does this idea make sense? Like, you give me a training set, you give me some new point, right? You give me some new point, and I will make sure to give you back all the distances from that new point to everybody in the training set. I've generalized everything that we just did with Alice, where we've kind of generalized over Alice. Okay, and because new row might be a piece of a table, we should also make sure that our distance function only works on arrays. So we should turn that one into an array as well. Something like that. I think that looks good to me, but what that will do, that generalizes the process that we just did. So if I say all distances now, we have like the entire CKD table maybe. Let's use that as our training set. Find them all to Alice. And then does the whole thing all over again. Starts with 116. It's this entire process of finding all the distances from everybody in this first table to this point. All right, with those attributes. And for attributes in this data set, we're talking about hemoglobin and glucose. That's what we're using to make predictions based on. Questions on that? So I've got a function that does that for me now. That's great. I can call this array, let's call it distances or something, so we can tack it onto the table. Boop. So now I have that. And so if I have my CKD table, my goal, right, is to attach the distance from everybody to Alice. This is what I want. I want this exact picture that we drew last time. Give me this distance to this new point so I can sort by that and find the closest k things. So CKD with a column, we'll call it distance from Alice, our example person. Distances can go there. And then we can call this something too, CKD with distances. So we're trying to predict, does this Alice person with those particular attributes for hemoglobin and glucose that she had, does she have chronic kidney disease? And so for everybody, we've got the distance from everybody and their attributes to Alice attached to the table. Is that clear what we just did? Because the last piece of the puzzle is to sort, get the top k, whatever our k was. So let's figure this out. Let's see, because class 1, these are kind of far away from Alice and they're all class 1. Maybe that means she doesn't have CKD. We'll find out. So let's sort this table now by distance from Alice. Just like that. And, ooh, it looks like it depends on if we use k equals 3 or 5. Isn't that funny? So if we use k equals 1, we're going to predict class 1. That's the closest person to Alice. We'll predict that she has chronic kidney disease. If we use k equals 3, we'll get these top 3 people, right? 1, 1, and a 0. The 1s win still. We'll predict that Alice has chronic kidney disease. But if we go k equals 5, and this is why you got to play around with a bunch of different values, it looks like then the 0s win. Then maybe we're going to predict that Alice does not have chronic kidney disease. This was also just a contrived point that's not really a good value. I don't think anybody has 0 hemoglobin like Alice does here. But that goes to show that that's interesting, right? So, okay, whatever your k was, some odd value, you want the top k rows of this table, right? So after you've sorted, you want the top k rows so that you can make your majority vote decision. So you say dot take, you give me the first k rows, and you can like take indices 0, 1, 2, 3, and 4. You can use a range for that, right? A range 5, the first 5 indices, and that will give me the first, because this is your k now. Whatever you put here is your k. This will give you the first 5 rows of this table sorted by distance. And now we want to pick out the classes and have a majority vote, right? Pick out the classes, have a majority vote. We are so close. Kind of what we want is like this gives me the k nearest rows, right? So let's call this, let's turn this process into a function again. Let's say nearest. This is a function called nearest. You give me a training set. You give me some new point that you want to predict for, right? Predict a class for. You give me a k value. How many, like what you're doing k nearest neighbors, what is your k? And then what we want to give back is this table of the top k closest points to that new point in the training set. Returns a table of the k, returns a table of the k rows with distances attached, having the smallest distances from the new point. Okay, whatever that was, this new person that we care about. So, okay, how did we do this? How did we get all this? The first step was we found all these distances with this all distances function that we made. That's good. So let's steal that. So get everybody's distance from this training set to this new point, right? We'll call it distances to new point. So use our function that we just made. Attach those distances to our table, right? Just like we did here. Attach it. This is our table with distances. It's not about CKD anymore. It's whatever it was with distances now, right? There's your training set with a column. We'll just call it distance. And you're going to put the distances to the new point into there. You're following me so far? We're just generalizing what we did. Have it work for anybody. And then we got to sort, right? We want to sort by the distance. We can do it all in one swoop like we did here, but might as well just split it up. We sort by distance, right? We can call that something. Sorted by distance. So we've now sorted by the distance column. That's on the with distances table for this function. And then we want the k nearest neighbors. So we take k, whatever k was given to us, k many from our sorted table, right? Just like this is a take np.arange, whatever. So this is our nearest neighbors table. We're just generalizing what we did. Take that, everybody sorted by their distances, and take the top k, np.arange. If it was 5, put 5 there, but it was k. Whatever the k was given to us, take the top k, and then return that nearest neighbors table. And that'll do it. If you want the 5 nearest neighbors, you say nearest. Or you use the entire CKD table as a data set, use Alice as a training set. Use Alice as our new point. K equals 5. That should do exactly what we just did. And it did. Though we call it distance rather than distance from Alice, of course. Does that make enough sense? All this generalized? Working all over again? That's pretty neat.
Slow conversion. You gave the specific example. It's slowly.
Well, thank you. This is fun stuff. This is an exciting lecture. So, yeah, that's how we're working with stuff. Let's see here. Yeah, we can call this something. Call it 5 nearest neighbors. Boop. And then I want majority rule. I want to know what class do we predict Alice to be now. So we're going to go to the class column and look and see who wins, right? It's going to be 0 or 1. Let's just assume it's always 0 or 1 no matter what table. Like that's the default format of whatever we could be given. We're going to have to go and count now, right? Go and count the zeros, go and count the ones, see who wins. Take a majority vote, greens versus blues. Who wins, all right? And that's why we used an odd k for sure. So how do we do that? Well, we have this table. if we go to the class column, right, 5 nearest neighbors, give me the class column where it's 1, give me the class column where it's 0, right? Where class values are equal to 1. That'll give me all the 1s, and how do I know how many 1s there were? I can just count the rows, right? How many rows did I get back here? Dot num rows. It's a little wordy, but that's one way to do it. These are the 1s. I do the same for the 0s. 0. I can't remember if there's an ES or it's just OS. We'll find out. So that's how many 1s, that's how many 0s, and just like who wins, well, I can do an if statement. If the 1s are bigger than the 0s, then I can print that the 1s won. Otherwise, I will assume that k was odd, and so it must be that the 0s won. It must be smaller, it could never be equal to if it was odd, an odd number of values. I'll print that 0 won. And then who, right, what's about to happen? Is it 1s or 0s? It's 0s. Isn't that fun? And that's our majority rule kind of calculation. Does that make sense? Questions about that? All right. So let's turn this. We want to make a function that does, like, this is our goal, right? Give me this function. Do the whole thing for me, please. So we're just building up little functions to get our way there. Let's turn this idea into a generalized function. Give me the majority rule for some nearest neighbors table. So I'll call it majority. You give me a nearest neighbors table. Assume that your classes are only 0s or 1s. Let's do this exact process where instead of printing, let's return. Let's return back what we were given. Was it a 1 or was it a 0? So this is you give me any nearest neighbors table, find the 0s, count the 0s, count the 1s. If 1s are bigger than 0s, return that 1s win. Return otherwise that the 0s win. And so if we were to now give this function our 5 nearest neighbors, it should give me back 0. And so we're so close, right? We are so close. We just got to hook all of those functions together now, because majority is kind of like the last piece of the puzzle. So I do get 0 back. Do you kind of see how we could combine majority with the function that creates the nearest neighbors rows to do the whole thing finally? Isn't that beautiful? So yeah, that'll give us our KNN function. Well, let's make it happen. Where do I want to be? So KNN, you give me a training set. You give me some new point that you would like to predict the class of. You give me k, because k nearest neighbors needs some odd number k. You could probably check against and make sure it's odd. Throw an error if you see that it was even, but we'll just assume that the user's fine and doing this correctly. What do I need to do to run k nearest neighbors? It's this process. Find the k nearest neighbors, take the majority vote. We've got a function for each of those now. So give me the nearest neighbors by calling this nearest function that we made. Just like we did here, give me the 5 nearest neighbors. Just give me the k nearest neighbors now. Instead of 5, give me the k nearest neighbors. Or just call this nearest neighbors table. Call nearest on your training set. Try to find the closest thing to this new point that you care about. And you're taking the top k. All right, top k things, whatever they were, generalized. And then the last thing we need is, okay, here's our nearest neighbors table. Call majority on it. Have the majority rule. Whatever this was, it'll give back a 1 or a 0. Oops. It'll give back a 1 or a 0. And if it gives back a 1, return that. If it gives back a 0, return that. So return whatever this thing's result is. And it's 2 lines to do the final thing that we care about, but it took a lot of intermediate work, didn't it? So now I can finally say, all right, k nearest neighbors, I would like to make a prediction for my chronic kidney disease data set. I would like to predict for this person, Alice, with her hemoglobin values and her, whatever the other one was, glucose values. And I like to use 5 nearest neighbors, please. And it does the entire thing, and it gives me back a label for where we think Alice should be. We don't know what she is, but at least this can inform the doctor or something. This is compared to other people in our training set. Here is what we think Alice should be. Here is, we found the 5 nearest points nearest to her in this space of glucose and hemoglobin values, and we've taken a majority rule over all those things. And it looks like the zeros went out, so we're going to predict that Alice does not have chronic kidney disease. Good for her. Hopefully. Yeah. So all these pieces together made up the k nearest neighbors algorithm. Are there any questions about how we made them all? Was it clear enough? Do yell at me. So let's see, I'm almost ready to ask you something, but I want to also do one other just baked out example, because now we got a function that does it very quickly. I've got another data set from the textbook about like classifying wines. So that's interesting. As we live in the Central Valley. So let's do k nearest neighbors on a wine data set. Boop. So do you remember that, well, here's our table, first of all. Table. It's just called wine.csv in my data folder. And here's some example wines. Oops. Some nice researchers have taken a lot of data on a bunch of different wines. You've got alcohol content, different kinds of things that appear in wines like minerals. I don't fully understand what most of these are, but hue, I assume, is what color it was in some sort of scale that's just a single number, maybe on a color wheel.
I believe the hue is directly related to the alcohol purity.
Oh, is it? Okay.
Yeah, and it's supposed to be the higher the purity, the more transparent it is.
Oh, so it's transparency versus opaque. Ah, interesting. Thank you. That's good to know. Yeah, so we've got all this data. They took a bunch of data, and we would like to use this to predict what kind of wine, like we get this kind of data from somebody else, let's use it to predict what kind of wine we have. Like we're not sure, we have some mystery wine. What kind is it? One thing that they do have in this data set is they have more than 2 classes. It's not just 0 or 1 anymore. It is 1, 2, and 3. I don't even think they have a 0. So we're going to need to change around some of the stuff that we did, because we're kind of, what we've learned to do is predict between 2 different classes. You can imagine that there's a way to do it for any number of classes. You still find a majority, but for the level that we're on in this class, let's just try to predict whether or not the kind of wine was the class 1 or something that wasn't class 1. Okay, so we'll focus on, was it class 1 wine versus the rest. And so I'm just going to apply a function to the class column that turns the 1s back into 1s and the 2s or 3s into 0s because they weren't 1s. So I'll make a function called was it 1? So if this value that I'm looking at was 1, return 1, keep it 1. Otherwise, call it 0 instead. And so now I'll turn the wine table into that. So wine dot with a new column, overwrite it because I'm going to use the same name, call class, and it's wine.apply is 1 to the class column, which is column 0. And if I do that, then I've turned it into 1s versus 0s. And if I really quickly do that and overwrite it and take a sample, it should work. Now you see that everything's 0s and 1s, just like we made our function to do. So we're just predicting, was it type 1 wine or some other kind of wine? Okay, that's what we're about to do. And our goal is to use everything but the class. Like all these values, these are numbers, right? We can put them into space. This is like how many columns are here? There are 14, if you don't count the class, there are 13 columns. And so if we plot these, it's hard to imagine as a human, these are all in like a 13-dimensional space. And we want to plot a new wine in a 13-dimensional space because we want to keep all these numbers. All these numbers are important. We want to use them all. So we would like to find distances for a new wine to all these other wines in terms of, like, this is an x value, this is a y value, this is a z value, and then make up new coordinates. So 13 dimensions, we want to find distances. This generalizes our distance function works no matter what. So let me prove that to you. I'll put that up here because we're going to need that. We're going to need that. So distance, our distance function works no matter the dimensions. That's great because of the way we made it using the NumPy library, working on arrays of things. Where is our distance function? I'll just rewrite it again. Distance, distance, distance. So here is our distance function. It was making use of arrays and just summed however many elements there were. And that was the trick. Oops, so it was supposed to be up here. So there's my distance function. Look at what we can do. So distance, we were doing it on like arrays that were of size 2. Like 1 and 2, compare it to what's the distance from the point 1 comma 2 to the point 4 comma 5. It's apparently that. But this still works, as long as they agree, at least. This is now 3-dimensional distance calculation, and it still works because it's doing subtraction on arrays, squaring of arrays, summing up all the elements in an array. Isn't that great? So it's happy. And so distance will work even if we give it a 13-dimensional value. And we can go and we can find the distance from all these guys, treat this like a big coordinate, to all these guys, treat this like a big coordinate. And they should be decently far away from each other in theory, because their classes are not the same. Yeah? That's what we like to do. So are there any questions about the goal right now? Like, I've got this wine table. There's zeros and ones now, of course, for the class. But I'd like you give me new values. Like, you give me some new wine. You don't know what kind it is. It's either 0 or 1. Give me the alcohol content, the malic acid or malic acid content, ash, however you pronounce these words that I don't fully understand. You give me all those, we'll try to predict, was it class 0 wine or class 1 wine? Okay, that's what we'd like. And so the attributes with which I'm going to compare wines to other wines is all this stuff but the class. That's what we call attributes. So wine, the attributes only, attributes, that's wine, drop the class column. And then that's legitimately everything but the class. All these things. These are things we want to compare against. And so now I can use my distance function to compare. I can compare row 0 to row 1. Or no, let's compare row 0 to row 1 because they are both let's just look at the wine table real quick. There it is. So yeah, row 0 and row 1 were both class 1, so their distances should be pretty small in theory. All right, they're both class 1. So let's calculate the distance between them. All right, so distance from row 0 to row 1 of this table. So we go to wine attributes, not counting the class. Row 0 and wine attributes row 1. But remember that our distance function only works on arrays, so I have to turn each of these rows into arrays by doing np.array on them. Boop. And it worked. Apparently the distance between those two wines is 31 units in this 13-dimensional space. Does that make sense? The distance function is comparing. It's comparing 13 values to 13 other values. It's like plotting, all right, go this much on this axis, this much on this axis. 13 axes total. It's comparing a ton of values at once. And both of these rows were class 1. Let's go find let's go find a row that was class 0. I did this ahead of time. If I go to wine.row 177, that one's class 0. So if I compare like row 0 to row 177, in theory I should get a distance that's much farther away than this one. And that would at least tell me that maybe k nearest neighbors is a good idea, because wines that are different classes are farther apart in space, in this 13-dimensional space. Let's try that. These will be class 1 and class 0. This is 177 to row 0. So this is class 1 versus class 0. Well, let's see what happens. Okay, this seems to indicate that maybe k nearest neighbors is a good idea, because the distance between a class 1 wine and a class 0 wine was 506 units, and the distance between two class 1 wines was much smaller than that. That's good, all right? And we do want to use all 13 of these attributes. Like we would like to use everybody to get the best separation. That's really nice, because if you use just a couple, let me show you some of that. Do apparently flavonoids, if that's how you pronounce that. Flavonoids, maybe. To alcohol. Group by class. If you try just 2, like we were doing for the chronic kidney disease stuff, you see how there's some, like there is a decent separation, but like these points right here, you're gonna mess up. You're gonna mess up for them. So you're not sure what's what. Same with the others. So it's good to use as many attributes as you can. Apparently also alkalinity of ash. And then there's just a column legitimately called ash. Again, there's kind of a separation, maybe here, but there's a lot that they don't agree on, right? That these 2 values alone cannot give you a full accurate picture of the differences, right? And so 1 more, because your book did 1 more. This is just proving to you that we'd really like to use all the attributes at once, if we could. Magnesium, total phenols. Again, kind of a separation. The blues are kind of lower than the yellows, usually class 0 versus class 1 wines, but there are a lot of places where they disagree, right? But they're not sure, at least. So there's a bunch of overlap. That's what we just found. There's lots of overlap. You just consider 2 at a time. But multiple features / attributes at once, rather than just 2 at a time, can usually make it work for you and often do the trick. Because maybe magnesium and total phenols couldn't agree, but like in this graph it was separated, those ones that couldn't agree. So like if we used 4 attributes rather than just 2, let's just use all 13, all the ones that we've got. Okay, that's what we'd like to do. So let's see if this works. Let's do k nearest neighbors on our wine table. All right, let's look at wine row 0, where our wine table is class 1 wine. It's got all these values for these different attributes. Let's go find the 5 nearest wines to row 0 wine. It's going to find row 0 again if we don't get rid of it, but let's forget about that for a second. So I've got a nearest function, right? Our nearest function took the table, that's our training set. Let's just pretend the whole data set is our training set. And then if I compare it against its wine attributes, right? That's everything without the class, row 0. Now let's do a 5 nearest neighbors, please. So it will find, like, distance 0, of course, is the original wine. This row 0, it's finding it within itself. But these are all the other ones that are close to row 0 wine. They're decently close with very small distances. And look at what their classes are. They're all class 1s. So this is, again, giving us firepower and proof that k nearest neighbors is a good idea. These different attributes really do separate the different classes of wines, in theory. So that was a class 1 wine. It looks like it's close to other class 1 wines. And then we remember that row 177 apparently was a class 0 wine, right? Or, yeah, class 0. Not 1. Yeah. It was 2 or 3 in the original data set. So there we go. Let's go find the nearest ones to it. Let's make sure this is going to work out for us. 5 nearest neighbors to class 0 wine. Of course, well, really there's 4 real ones, because you get the original wine is distance 0. It is itself, closest thing to itself, if you don't get rid of it. And then we find 4 other class 0 wines decently close to a class 0 wine. So that is giving us some proof that k nearest neighbors is going to do a good job in this 13-dimensional data set on wines. That's good. So that we can build a classifier out of that. Does that make enough sense, what we can do now? Because this is our goal. we're going to split up now our training. We're finally going to do it right. We're going to split up our original data set into a training set and a test set. We're going to generate our classifier using the training set. We're going to make predictions based on only the training set, and we're going to test it on the test set. You give me some more wines that we've never seen before, plug it in, get class 1 and class 0 out of our classifier, and then we can compare against, because we're going to hide away like the real class of this secret wine. We're going to see, was it really class 1? Was our prediction correct? All right, so let's make a legitimate training set and a test set and test and make sure we did this right. Okay? Does that make sense? What we'd like to do? And then we can test and see if it worked. So let's at least figure this out. Because yeah, our goal is to figure out, like, we want to make a classifier legitimately using a training set, save away some stuff with a test set, and make sure that it all worked out. So this is our goal now. So we would like to use, right, we're going to split up, make a training set, make a test set, and then we want to test everybody in the test set using the training set. Test everybody and see if this all worked out. So we're going to make, where am I? We're going to make our k nearest neighbors classifier, our black box, using the training set. And for each piece of the test set, we're going to plug it in, get a class out. Like, all right, the first thing was class this one. Second thing was class this one. The third thing was class this. We're prediction. And then we're trying to see, were those classes the same as the classes listed in the test set? Were those equal? Because if they agreed, that means our prediction, our classifier, is doing a good job. So that's question mark this. Is this actually working out? Are those actually equal? Okay, that's our goal right now. Maybe I should draw that in a different color. Are these equal? Question mark. That's what we'd like to do. So let's at least get that far, and then we'll talk about it. So I would like to evaluating the classifier's accuracy. So we got to split up our wine data set. So we got a big long wine data set. How many rows do we really have? We got 178 rows. So usually you make your training set a little bit bigger than the test set. That happens in practice, but why don't we just cut it in half? Half of the wines are our training set, half of the wines are our test set. So like just take the first 89 for one set, take the other 89 for the other set. But remember, we want to have like every possibility. Like we would like a random sample for the training set and a random sample for the test set, because in order right now, I think it goes just everybody class 1 and then everybody else was class 0 at the bottom. So like we're not going to have any class 0 wines in our data set probably if we just take it in this order. So we should shuffle. Let's shuffle this data set to get a random test set and a random training set. We better shuffle first. Boop. So yeah, let's make a shuffled wine table. So to shuffle the wine table, you take a sample of the wine table of all the pieces, all the rows, without replacement. With replacement equals false. And that's my, oops, I put a minus sign on that. So now I've got zeros and ones in the first few rows. That's great. Different every time. So this is my shuffled wine data set. And now I can make a training set out of it, and I can make a test set out of it by taking a few pieces, a few rows. So let's take the first 89 rows for the training set. Take our shuffled wine set and take the first 89 rows. So take the first 89 range. Take the first 89 elements, so indices 0 to 88. And then for everybody else, you're going to take it to starting at 89 now, going up to 170, I think there's 177. 170, yeah, there's 178 total, excuse me. It's 10 more than that. 178. So index 177 then for the test set. And so now I've got two completely randomly chosen training sets. I've cut my original data set in half. I'm going to make my classifier with the training set. I'm going to test it with the test set. So my training set is only 89 rows, got zeros and ones in it. My test set is also. Completely different lines. We're not having them share. Again, 89 rows. And we're going to see, did it all work out? All right? Did it all work out? So we're going to, yeah. Does that part make sense? We snipped up our data set into a training set and a test set. We're going to make our classifier using the training set and test it with everybody in the test set. So I do want to talk about that bold word on the slide, but I don't know if we're ready for it yet. Yeah, let's do it at the end. So what I'd like to do is get predictions for everybody in the training set and compare it to the classes. For everybody in the test set, like hide away, cover up the class column, feed all these guys into my classifier using the training set to make the classifications, and then see, hey, was the first one class 0 actually? Was the second one class 1? Because these are what they need to be. Let's see if they actually ended up like that. So yeah, what we can do is we can just use our equals, our equality checks on arrays, because we're going to get back, like, we can take the class column that looks like an array, looks like this, right? Make array 0, 1, 0, and so on. We can go and see if, like, was that equal to what our classifier gave back? It'll also give back, let's make a function that kind of gives back for each point, for each row, what the class should be. So I'm going to get another array just as long of our classifier's predictions, like maybe it's wrong sometimes. And we can get a bunch of arrays of trues and falses. We can get one array of a bunch of trues and falses. Like, hey, did the first ones agree? Did the second ones agree? So like we've got the original classes, like 0, 1, 0, and we've got our predicted classes from our classifier. And we just count, right? We can count and see like what was the rate at which we did this right. Yeah. So that will end up, if we were able to do this, we can get a good, like a percentage accuracy for our classifier. So we can use double equal, remember, on arrays to test the original classes against the classifier's best guess. And then I can finally give you a question. I have to build it all up. Okay, so yeah, we've got all this. We can, how do we get a rate? Remember that trues in Python are 1s secretly, and falses are 0s. So if I got an array of 0s and 1s secretly, if I just take the average, I can do things. Or I can also count non-zero, right? np.count non-zero. How many things are 0s? How many things are 1s? Where 0 is false and 1 is true. There are 2, and I can divide by how many things there are by the 3. So that can give me a rate of how accurate it was, right? So kind of what I want to do is I've got a training set, I've got a test set. I want to make a function that kind of gives me an accuracy percentage for like comparing everybody in the test set against the training set. So I want to make, like, my goal is make a function that looks like, make this function. I want it called, let's say, like, evaluate accuracy. And here's my training set. Here's my test set. Go inside of the test set, test everybody against the training set. And my k value for k nearest neighbors, let's make that be 5. All right? That's what I like to do. Okay? So let's make that happen. Because I can call, right? I can call k nearest neighbors on this entire, every piece of the test set, right? By doing this. I can get, I don't want to have the entire test set at the start. I only want everybody but the class. I want to hide away the class, see if we predict the correct one. So I just want the attributes again. So test attributes is everybody but the class from the test set. Boop. So I got everybody but the class now. And watch what I can do. I can remember that for the test set, the first one was class 0. So if I use row 0 of the test set and do KNN on it, use my training set that I made, take my test attributes table, everything but the class, row 0, that was a class 0 thing secretly, use 5 nearest neighbors, it is predicting 0. So it was right. It did it right for the first one. But now I want to check it for row 1, for row 2, for row 3, row index 4, row index 5. Let's see how accurate this was. See how often it gets it right. Does that idea make sense? Like I want to do this for every single piece of my training set. Hide away the class. Here I've hidden it away. See if using the training set to predict the class for this row is accurate. And so, yeah, let's kind of make a function that does this to every single row at once. That's my goal. So I can say something like, take my test attributes, apply a function that like classifies every test row, and then we'll see what happens. All right, so let's make a function called classify test row. So you give me a row of this table. I will do k nearest neighbors on that row. So return whatever this gives me back. Okay, using the training set on this row, using 5 nearest neighbors. I want to apply that, and look what happens. I get a bunch of zeros and ones. Like the first one is predicted to be class 0, the second row is predicted to be class 1. That is correct. The third row is predicted to be class 0. Oh, sorry. No, the second one's predicted to be class, 0, even though it was 1. So we got that one wrong. And that's okay. It happens. So, but the third one, predicted to be class 0, that was correct. Eventually, we're going to predict a class 1 correct. That was this one. There it is. But do we see what's happening? I am trying to make a prediction for everybody in the test set. I'm covering up the real class. And I'm using all the attributes to make the prediction using the training set. And we're seeing, did the classifier do a good job? Sometimes it gets it wrong. Like this one was 1. We're predicting 0. It's not always going to work. Maybe with a bigger data set, this would have worked out better. But is not horrible. It seems to be doing the first 5 more or less right. It's missing 1 out of 5 of the first 5. So let's see. Let's see what happens. Let's see how often it was equal, right? So like here are the predictions. These are the predictions. Let's see if they're equal to the real classes from the test set. So test set, go to the class column. And so the trues are when it got it correct. So like it got the second one wrong, but there are a lot more trues than falses, you see? And so to figure out how well we did, what's our accuracy, we can do this kind of calculation, like how many times did we get a true divided by how many things are here. So do a np.countNonZero for all these. So there are 80 trues out of how many? It's like 89, I think, right? But we don't have to remember. It's a test set. How many rows are in it? And it looks like our accuracy is about 90%. That's a decent classifier. That's great. Isn't that fun? Are there any questions about this process? I've just that's the whole point of making a training set and a test set. We're using the training set to generate our classifier, and then we save some stuff away in the test set to make sure we didn't just memorize stuff. We use every single row of our test set, forget about the class for a second, give all the attributes to our classifier, using the training set to make the classification. Hey, what class do you think this is? We think it's 0. Okay, that was correct. Hey, what class do you think this is? Okay, the classifier thinks it's 0. Oh, sorry, that's incorrect this time. But you move on down the line, and it looks like about 90% of the time it's doing the right thing. Isn't that neat? That's pretty powerful and cool. We were able to make that in a day. So let's see. Our goal is to make this kind of function. You just do all that at once. Give me this accuracy percentage. So let's make that function. Evaluate accuracy for a k value, whatever it was. So what do we want? How do we make this happen? Well, where in the world did I say that we want? Okay, so yeah. First we started with the attributes of our test set, right? So just the stuff without the class. So we made that because that's what we give, only the attributes for each row of the test set to our classifier. And then we wanted to do this for everybody, right? Or, yeah, and then also give back a number. So we'll do that in a second. So here's all this. This is that. Classify test row. This is the k that we were given. This is still correct using the training set. And for some reason, you don't have to call these what they were because they're just parameters. So like apparently in my example, I called these just training and test. So this can be called test. This is just called training now. And And then what do I want to do? I want to make predictions. I want to make these kinds of predictions that was applying classified test row to everybody in the attributes. Now, these are our predictions for everybody. Predicted classes. That's all these numbers, which I got rid of because I did the equality, but we've made predictions for everybody. And now I want to see how often were our predictions correct. So we're going to look at our predictions and then compare them against the test set's actual class column values. Okay, it was really class 0 for the first one. It was really class 1 for the second one. But compare against, this is what we predicted, this is what they really were. Give me a percentage. So how many trues were there after this comparison is complete? Divide by how many rows there were in the test set. How many predictions did we make? And then return that answer, and that is a function if I didn't mess anything up. I can take my training set, call it training, take my test set, call it test, and give a k-value, let's say it's 5, and we get the same exact answer back because for every row in the test set, it hit the class column. It's like, all right, use the training set to make the prediction, then actually look at the class column. Okay, was it right? Was the prediction correct for that one? Check. Was it right for this one? No. X. And it keeps on going through. And yeah, that is classification and accuracy analysis in a nutshell. Does it kind of make sense how we got here? There's a ton of functions just working together right now, and this will definitely be something to study. This is a very exciting chapter, but it's also a decently complicated chapter. It's building on top of anything and everything we've talked about so far in the entire semester. So yeah, I hope you find it exciting too. Are there any questions about anything up to this point? So you can make a classifier now. You get a data set. You can predict a categorical variable. And by the way, your accuracy depends on your training set and your test set. So like if you do this on your end, you're going to get a different accuracy most likely because it depends on the randomly chosen training set and the test set. Like in my notes, I got a 91% accuracy. It's not exactly the same, but it's always going to be decently close if it was a random sample.
You're also randomly shuffling.
Yeah, every time it's random, exactly. And so, in theory, it will always be kind of close to 90, we'll hope. But you can get a very bad sample probably with just all class zeros and you don't know what a class 1 is anymore. But yeah, that's that. The whole point of doing this, setting some stuff aside, is so that I kept saying memorize. We don't want the classifier to memorize the training set, right? Because then it will just spit back out what it thought when you give it the test set and it has no clue about anything. That's called overfitting, all right? And so I guess I should read this bullet first. So first of all, you better hope that your training and test sets are good, right? When you split it up, you should be shuffling randomly just to make sure you've got a decent spread of the different classes within each of those. They should accurately represent the population because otherwise, like, it's not going to work out. If like you have nothing but class zeros in your training set and nothing but class 1s in your test set, you're not going to learn what a class 1 is, right? You're not going to figure that out. So that's important. And then, yeah, the whole reason you're setting some stuff aside is to make sure you didn't, the technical term for memorization is called overfitting. That's when your classifier, it's doing really well on the training set. You compare it against the training set, but it really just memorizes stuff, right? It can't do well on that test set because those are actual new values and it really needed to learn something and it didn't. It was just memorizing rather than doing machine learning. It's machine memorization. All right. So that is the moral of that story. And that's why we split it up. All right. So you have a bunch of functions. I'm going to give you those functions, but I would like to spend probably the rest of the time today on this question. All right. So we have another data set from the textbook on breast cancer this time, and we're going to look at the data, and then I'd like you to do exactly what we just did for the wine data set. I'd like you to train and test a k nearest neighbors classifier where we picked k to be 5 again and see how well for your particular training test set split your classifier does. So let's go look at the data real quick. And so you can imagine like you get numerical data like this this can save people's lives, right? You can very quickly go from a what's the word? It's like a screening, and then you can alert the doctor if something looks like someone else in this data set who had breast cancer, for example. So it's called breast-cancer.csv in my data set, and these are my patients. So here's a sample of them, and it's just nothing but numerical values. So class 0 is they didn't have breast cancer, class 1 was they did have breast cancer, and then here's a bunch of different numerical values related to an exam that got done. The ID is just like it's like their student ID, you can imagine, just an ID of the patient in their little medical database. And so we don't want to use the ID, first of all. Is that clear? Like, we don't want to be comparing IDs to IDs like that. That is a numerical data point, but it's completely useless to us because everybody's ID is different. It'll just put people farther. Like, it makes no difference that these two IDs are slightly closer than these two IDs. Okay, they have nothing to do with whether or not this person had breast cancer. So the ID is not something we should be using to do our comparison. So I will drop that ID column. So these are my attributes, and then here's the class. Everything but the class is the attributes that we're gonna make predictions out of, right? So we've got how many columns now? We got 10 columns, so 9 attributes in one class, right? One class column. And then how many rows do we got? Oops, I spelled rows wrong. 683, nice. And among those patients, how many had cancer, how many didn't? So what kind of data set do we have here? Group by class. It looks like we had 444 non-breast cancer patients, like all these data, like they got their examination done, and it turned out they did not have breast cancer, and then 239 of them in this group, they had it. And let's take a look at some of these things, some of these different data points. Again, we want to compare against all of them at once, but let's just prove to ourselves that that's a good idea again. Let's scatter over on the X, whatever this is, and single epithelial cell size, whatever that is. I am not a biologist. Group by class. And so, all these numbers are like hard numbers, like it's 1, 2, 3, it's whatever the doctor gave it. It's not, there's nothing in between, they're all integers. But there's kind of a split. But actually, what's happening right now is you see that some of these dots are like gray. They're in between blue and yellow. That means there were a bunch of people right there. The darker it is, the more blue it was. Like this one had more blues than yellows, but this one had more yellows than blues. Like they overlapped here secretly. And the term for this, and this will happen when you have integer data like this, a bunch of these dots, they're overlapping right now, so we can't actually see the full picture. A bunch of dots overlap. And this is called overplotting, apparently. What happens, when this happens, we call it overplotting. You're plotting points on top of points, and that's not good. So here is a silly thing that your textbook did. You do not have to understand this, but let me at least show it to you. I'm just going to copy and paste the code. It's cool, though. Here's what you can do to solve that problem, to actually see what happened, what was really there. What you can do is, instead of plotting the points exactly there, you can kind of like randomly squish around, randomly jumble around those points, around the integer coordinates that they're at. So your book calls it, they're jittering the points around, which is kind of cool. And so you can kind of now see where the overlaps are, because like you're randomly like shooting points off in different directions around where they came from. I assume they're using a normal distribution. So you see, like, it's kind of all over the place. So you couldn't just use those two again, but you could use every single attribute to make your prediction And that's what you want to do here, all right? So are there any questions about this data set or the wine example before I have you try this? Because what I want you to do is what was written on the slide. So your example, your crushed ice of the day is shuffle. I'll give you all this code in just a second. Shuffle the patient's table. Make, let's do a training set and a test set. Do a 50-50 split like we did for the wine example. So you can copy and paste a lot of code. 50-50 for the training / test sets. And evaluate the accuracy of use a 5 nearest neighbors. So K is 5 for K nearest neighbors classifier. And see how well it went. So let me give you all this code. So you refresh the code from class page in 10 seconds. You should now see our updated chapter 17 file. In theory, yes. Give this a try. So go get my breast cancer.csv file. We looked at the table and do exactly what I did for wine. You're going to have to read in all those functions. So you probably just press play and you have to use the eligible file. Otherwise, you have to copy and paste them in. So like, you have that evaluate accuracy function, which depended on the KNN function, which itself depended on the majority function and the nearest neighbors table function, all together. But I'll give you a few minutes head start there, and then I'll do it too. But let me know if you have any questions as you're trying. But this is really satisfying to get and see, like, hey, did this work out well? Because this is saving people's lives, right? This is exciting.
That's exactly what we do for doing neural networks and AI.
Yeah. This is as close as we get to neural networks kind of in AI in this class. Yeah, we got plenty of time, so I'll give you a few more minutes to try it. But honestly, it all is like once you got all the functions defined, you can just kind of call evaluate accuracy, that function that we made on it all. But you have to split it up first. You got to make the training set, you got to make the test set, just like we did for the wine example by chop it in half after shuffling. And I encourage you to like run the cell twice, because if you make another random shuffled training set and test set, you're going to get a slightly different accuracy. Oh, sweet. Mm-hmm. I think a great way to study for this chapter would be to like cover up all the functions that we made and try to remake them. I'll give you a few more seconds on my timer to have a head start, but are there any questions that I could answer before I show you stuff? So I think this will be the last thing I want to do for the day. It's very loud.
Other than possibly naming variables differently, perhaps renaming a few columns, it's pretty much exactly the same code.
It really will be. So let's figure this out. If I want a 50-50 split, well, how many columns do I have? Or sorry, how many rows do I have? 683 rows. That is unfortunately an odd number. So we're going to have to make a choice here. Who gets more? I can't like have half a row in one, half a row in the other. So let's start with the shuffled, right? We've got it's called the patience table. Let's shuffle it by taking a sample of all of the things without replacement. By default, it's going to take all of the things, but we can explicitly say all 683 rows, please, with replacement equals false, so we don't clone anybody and delete other people. This is my shuffled patience table. And then there really is going to be a lot of copying and pasting from the wine example. So how did we get the training set and the test set for wine? We just took the shuffled table and took rows in order, because after it was shuffled in order doesn't really, it's a shuffled order now. So I would like,
That's using the other number. So you have to change
yeah,
it to
exactly.
your number.
Yes. Thank you. So okay, now we've called it shuffled patience, and we want, let's have a slightly bigger training set than a test set. Let's have 342 rows for the training set, and then we'll start there and go to the end for the test set. So go from index 300, so index 0 to 341 for the training set, from index 342 to 682 for the test set. Does that make sense, how we did that? You see it working?
Could you use the num rows to also
Absolutely.
cut it? Yeah.
Yeah, instead of saying 683 all over the place, I could have said that's exactly equivalent to, I guess it's just patience. Dot num rows. And that would make it even more generic. You could make a function that generates a training set and a test set. We might do that next time. Because it can find the num rows, it can cut it off. You tell me what kind of split do you want. Like, give me the percentage of things you want in the training set. Yeah. We could make even more functions than we already made today.
Then you could have that. Oh, I'm only going to use 10% for the training. See how bad it trains?
Exactly. Yeah, with a big enough test set or training set, maybe big enough sample, who knows? Let's see, and then we can, once we have this, our evaluate accuracy function works just as we had it. You give me a training set, you give me a test set, you give me a size, you give me a number for k nearest neighbors. We're going to choose 5. I'll evaluate that accuracy for you by trying I'll make a classification for every single row in the test set against the training set using the k value. And see how often did it do it right. And so I will call evaluate accuracy on training set. And we just called it test set We said K was 5 this time. And it looks like, all over again, did we get 89%. So very similar to the last one. If we do it again, it'll be something different. Oh, this one was 97% accurate. That was great. All right, that was a very good training set.
That's for sure.
Nice. Awesome. It is going to vary each time, but to have 97% accuracy in detecting, just based on numbers from an exam, detecting breast cancer likelihoods, that's a great thing. That's a wonderful thing that we have at our disposal. So computer science plus medicine is a very good mix. Data science plus computer science plus medicine plus machine learning, all these different terms. And yeah, I think that's a great place to stop for code today. Are there any questions about any of the code that we wrote? It might just be a matter of staring at it for a while, reading the chapter where they're going to talk about it too and write it out for you too. But it's fun stuff. Are you good? All right, I do want to wrap it up because we've been talking for a while, but let's give you a sneak peek of what we're going to do next time. We have done normal regression, right? We did linear regression. We had 2 dimensions. We were trying to find the best line through the data. We have a lot of attributes that are numeric for our data sets. Like think of the wine data set. It was like 13 things, right? Linear regression is finding a line in 2D space. There is a concept of a line in any dimensional space. It's called a plane or a hyperplane. We've taken like a calculus class. Maybe we've heard about that. So our goal for at least the start of the next example, the next lecture, is going to be, it's called multiple regression or multiple linear regression if we're trying to find something equivalent to a line in a hyperdimensional space. It's really cool. And so we want to find a really good line. That's what we learned how to do. We want to find a really good equivalent of a line in 13-dimensional space to make some predictions because we see that there's some correlation going on. All right, so that's what we're about to do. So we're about to find the equation of a line equivalent, line adjacent thing. Oops, what is that? Yeah. And that's how that's going to work. It's going to be great. So what we want to do is instead of finding a single slope, like the equation for this was like y equals mx plus b, right? This is like the best line that went through this. Like maybe it was this, I don't know. And that was an equation for a single line. And one of the key parts of that was finding the slope as well as the intercept. And yeah, so we need to discover the best slope and the best intercept for this thing so that we can make a prediction, right? You give me some other point around here, I can just feed it in, give me that x value, use my slope and my intercept to predict the y value, right? We kind of want to turn that into the same thing here, all right? The same thing here where we've got some, I don't know, output. I'll use a real example in a second, but it's going to end up being house prices. I'll show you that next time. But like we want to go from this to the idea of finding a really big line in multi-dimensional space where it's like you've got your x coordinate, your y, your z. People eventually start calling it x1, y, x2, x3. We want to try to find an equation like this that looks linear. It's just got a bunch of slopes. x2 plus slope 3 for the times the x3 coordinate plus dot dot dot. And maybe I should draw that in blue because it's a little hard to read in rainbow. But that's where we're going. That's where we're going to go next time. So sale, we're going to talk about house prices and how much they're going to sell for. So like the sale price of this house, given the square footage of the bottom floor and the top floor, and like how big is the backyard? Does it have like
how many bathrooms?
How many was the volume of the garage? If there isn't one, it'll be 0. Like all these values, we're going to feed them in.
So did you kind of already touch on it with your K dimension with the wine? Or is it actually a different algorithm?
It's going to end up being kind of K nearest neighbors all over again. It's going to look a little weird though. Yeah. what's the best way to explain it? So we want to find a bunch of slopes. Where did that go? Root mean square error. Oh, okay, yeah, it's gonna be actually similar to linear regression, where we have a function that's going to minimize an amount of error.
Okay.
We're going to minimize the amount of error for all of these different values at once. That's our goal. We have a function that can just do that magically for us in this class. That's very nice. Well, let's see here. But you could also feed this into k-nearest neighbors and you can compare. Like, this is another kind of prediction algorithm, which is cool in itself. So, all right, so that's our goal for next time. You give me some information about a house, like number of rooms, how big the garage is, how big the, I don't know,
Pool.
What's the size of the backyard, size of the pool, all these things. And we're going to predict slopes. How important are they in influencing the price of the house? That's what we're going to do. And it's really, this looks like a line, just a bunch of mx's for a bunch of different m's and x's. So goal, find a bunch of slopes instead of just one like we did for here. And I guess you could find an intercept too, but we're just going to not, and it'll work out just fine.
Probably because you're merging so many slopes, your intercept is getting lost.
Yeah, probably. I don't know. I was not trained in this, so I know just enough to teach it. But I assume that's exactly right. Yeah. But that's what we'll be doing next time, and that's the goal. So I'll put a little to be continued right here for us. Are there any questions about the stuff we talked about today or any of that? Any more? Because if we're good, that's where I want to stop. And let's make sure there's nothing left to do. Oh, there is something left to do because it's week 15. I want to talk about your final exam. So no new assignments, but we got to talk about the final, right? So we got a test coming up, and here's what I want to release. We've got, remember, I've said this a few times now. This is week 15. We got 17 weeks of class is, and then the 18th week is finals week. Right, week 18 is finals week, and so I'm going to release this week 18 module, at least a few pieces of it. We got final info, and with each test comes an extra credit assignment. So here, we'll talk about both of those. Eventually, the final will be here. You'll come to the class of the day of the final. We'll talk about that. You'll take it. It's just like it'll just be exactly the same kind of format as the midterm, just a little bit longer because finals are meant to be like we get 2 hours scheduled for that. So let's talk about the final. All right. So here is when our final is scheduled to be. It's going to be scheduled to be on the Wednesday of finals week. So it's technically as late as we could possibly have it. It would have either been on the Monday or the Wednesday because this is a Monday-Wednesday class. So we get it on the Wednesday, which is nice, which is the 20th, right? So a little under a month now. 1, 2, exactly 3 weeks away, right? So that's when it's going to be. And that means there is no class on the Monday. There is no class on the 18th. That would be, you might have another final at that time. So you don't show up on the 18th, but the 20th you show up in this classroom, and it's going to start at the same time as class. So it starts at 3, and here is kind of the logistics. So the topics are going to be these things, all right? We'll cover these homeworks and labs and projects. So I'm trying to hit harder the stuff that was after the first midterm, but you know that it's all like I'm still going to ask you about loops. I'm still going to ask you about let's make a graph or something. Stuff from the first midterm will appear, but I'm going to hit harder the topics from after the midterm. All right, so everything builds on top of itself. We know this, but this is I'm going to try to focus on those things. And then the format is going to be exactly the same as the midterm. In fact, I copied and pasted it, and I should change midterm to say final. Boop. The final. It will have the same kind of questions, fill in the blank coding questions, and you got to take it on the big computers. It's closed book, but you're allowed to have the following things, just like for the midterm, right? So you can have your cheat sheet. You can write whatever you want, as small as you want, as long as it's handwritten, both sides. You can have as much scratch paper as you want, and then you're allowed to go to these 3 tabs, nothing else. You can have a little blank Jupyter notebook open. You can look at our reference pages for the library that we're using, and that's about it. So that's what's going to be on it. Here's a sample final. This is the one I gave last time, so you can expect it to be similar to that. So go look at that, study with it, And I think that's all that I wanted to say about the final. That's when it's going to be, what's going to be on it. You have a way to study, and you know the format. Any questions about that? It's the Wednesday of finals week. That's when we had it scheduled. So come here, you'll take it, yeah.
The sample file that you're going to give us, is that going to have more like problems and questions than it's going to be on the actual test?
No, I'm going to try to keep it the same kind of difficulty for
But like, is there more practice questions? I guess that's probably the better way to reword that question.
No, this is legitimately the last final I gave for this class.
Oh, okay.
That's all it is. I didn't write extra questions or anything like that. Yeah. Other questions? All right. So with each test, I have an extra credit assignment. So if you would like to do this one is due midnight before the test comes out. So for test is on the 20th, this will be midnight on the 19th. If you would like, this is an excuse to study. This will be worth up to 5% extra credit. You can make another review video if you would like. Make a video going over stuff that will appear on the final, right? Don't go over midterm stuff, final stuff, please. You should have made a video for the midterm if you wanted to talk about that stuff. So just go over a bunch of examples, if you would like, of stuff that will appear on the final. Just like pretend to give a little mini lecture, like, hey, here's a classification problem. Here's a data set that I found. Let's write a classifier, something like that. That would be a great example, I think. And it's a nice way to force yourself to study. And yeah, so just make up some examples, go over some stuff, try to give a little lecture maybe, and you'll post it down here. So if you want a quarter of the extra credit, make a 10-minute video going over a couple quick things. You want half of it, make a 20-minute video going over like a more detailed problem or a set of problems that you came up with. And if you want the full 5%, please make a 40-minute review video where you go over a bunch of stuff. All right? And do remember that, like I said this last time, but you know, right? You got to do something extra to get extra credit. You can't just like go over an assignment. You can't go over my slides because I worked on those, not you, right? So make some new code, find a data set on the internet and analyze it in some new way. Make your own slides, draw some of your own diagrams. Let me know if you have any questions about whether your idea is right. But as long as you adhere to those thoughts, it should be fine. All right. But yeah, let me know if you have any questions about how to record yourself. I use OBS.
That's what I use.
Yeah, that's what the cool kids use. And then Zoom, of course, can also has a recording feature. But I'd be happy to help you get that all that stuff installed and working, because everybody should have an opportunity to do this if they want to. And yeah, so just like for the midterm extra credit assignment, this is a final exam. Make a review video for stuff that might appear on. And it'll be due the midnight before the test comes out. No late submissions for that one. Got to get it in on time. Any questions about that? All right. I think that's all that I wanted to say. So you know what's going to happen for the final. You'll come here. You'll take it on the big computers during that time range. And it'll be right here eventually. I'll make it available. All right, once I'm done working on it. I think that's all that I wanted to say. Yeah, I can stop the recording now, I think.